Hello and welcome back. Thank you for joining me again. Today we're talking about U substitution, which is a really important tool of integration. Basically, we're going to rearrange some stuff in order to integrate it. U substitution is a method of integration designed to undo the chain rule. It generally involves 3 steps. So here you have a function, f of g of x, g prime of x dx. So we have an outside function, we have an inside function, and we have the derivative of an inside function. Are you noticing the chain rule here? The key to U substitution is finding a piece of the function whose derivative is also in the function. The derivative is allowed to be off by a coefficient, but otherwise must appear in the function itself. Our 3 steps. Step 1, let u equal g of x, then du equal g prime of x. Now we have a new function, f of u du. Find the antiderivative of f, so you'll get big f of u, and of course your constant of integration. Then substitute g of x back in for u, and magically we have big F of g of x plus c. So A, look at A and see, what do we have here? We've got something squared. We've got something squared. What's being squared? X squared plus 1. And look at this. The derivative of x squared plus 1 is 2x. So again, the key to U substitution is finding a piece of the function whose derivative is also in the function. So we're going to say u equals x squared plus 1, and then take the derivative of that. Du equals 2x dx. And then check this out. Du literally is the same thing as 2x dx. And u is the same thing as x squared plus 1. So we can just rewrite this whole thing. We'll plug in u instead of x squared plus 1, and we'll plug in du instead of 2x dx. And now we have a new function. This looks much easier to integrate. Add 1 and divide by it, you get 1/3 u cubed plus c, and then put your u back in, and you're done. 1/3 x squared plus 1 cubed plus c. Let's try part B. U on this one is going to be 4x. That's an inside function. And its derivative is also there, 4 dx. Do you see that? It's split up a little bit, but it's still there. So now we'll rewrite the function as cosine u du. We can take the antiderivative of cosine, it's sine, and then plug u back in. So our final answer is sine of 4x plus c. Let's keep practicing. What do you think our u would be here? When you have a radical, check to see the whole thing under the radical. That's a good way to start. So if u equals 4x squared plus 1, what does du equal? Oh, look at 8x dx. So our new function is the square root of u du, or written in fractional exponent, u to the 1/2 du. Add 1 and divide by it, 2/3 u to the 3/2, and plug u back in. Part D. So here's our inside function, x squared plus 2. If we make that u and take the derivative of it, we get 2x dx. But that's not really in there. I have x dx up in the original and 2x dx down at the bottom there. But remember, the derivative is allowed to be off by a coefficient. Okay, so in order to get just x dx, I'll divide both sides by 2. Now I have my x dx matching. Okay, now the 1/2, I'm just going to pull that to the outside of the integral. And then I've got u cubed du. Add 1, divide by it. Okay, so my 1/2 is still on the outside. The antiderivative of u cubed is 1/4 u to the 4th. And then you can multiply that 1/2 back in and plug in your u. When you see something in fraction form, always look at the bottom of the fraction to see if you can find a u in the bottom that might work. An inside function on the bottom is 4x squared plus 3. And if you take the derivative of that, you get 8x dx. Pretty close to x dx, isn't it? Just off by that 8. So that's fine. We'll divide both sides by 8 to get x dx by itself. Pull the 8 out of the integral, and all we're integrating is 1 over u to the 6th, or u to the negative 6, add 1 and divide by it. So we've got 1/8 times negative 1 over 5 u to the 5th plus c, and then we can plug u back in and multiply the 1/8 times the 1/5. Part F looks like there's a ton going on. But let's look at an inside function under the radical right there. 7 minus 2x cubed. Take the derivative. You get negative 6x squared dx. But we want just x squared dx to be left over. So we'll divide both sides by negative 6. Now this is du, and our u is to the 4/3 with a negative 1/6 out front. Add 1 and divide by it. Put u back in and clean up your fractions a bit, and you're good to go. Integrating trig functions can be tricky. A lot of times you'll have to rewrite them before you can integrate them. So for example, tangent x dx. Well, we know that tangent x is sine over cosine. And then I always like to look in the bottom first to find my u, because I want my du to be on the top. So if I have u equals cosine x, du equals negative sine x dx. Oh, that's good. So just this negative has to come out. And then I have 1 over u du. Ooh, what's the derivative of 1 over u? Natural log of the absolute value of u, don't drop your negative, plus c, plug u back in. So our final answer is negative natural log, the absolute value of cosine x, plus c. Cotangent, well, that's just the upside down version of this whole thing. So this time, u is going to be sine of x. Du is cosine x dx. 1 over u du is going to give us the natural log of the absolute value of sine x plus c. So for part C, I've already started this by just expanding that sine x plus cosine x times itself. And if you'll notice here, sine squared x and cosine squared, if you add those together, what do you get? You get 1. Now what do? We're integrating 1 plus 2 sine x cosine x. 1 we can integrate, that's going to be fine. It's 2 sine x cosine x that's the issue. So we'll split that integral, okay? Now we'll let u equal sine x. What's the derivative of sine x? Cosine x. So look at u is right here, and then du is right next to it. Now this looks much easier to integrate. So 1 becomes x, 2u becomes x squared at our constant of integration, and then plug u back in. If we have a definite integral, we can also use u sub to make the problem a heck of a lot easier. When we integrate over an interval ab, the values of a and b are x values. The use of u substitution, though, requires ab to become g of a, g of b. In other words, they need to be u values. Let me show you what that looks like. Just thinking about our u substitution, we have an inside function here of 1 plus x to the third, so let's let that be u. And then our du is 3x squared dx. That's lovely, 3x squared dx. So we would have a new problem of u to the 1/2 du. Now we have to talk about our upper and lower bounds. So originally x equals 0, but everything in our new problem is in terms of u. So we're going to use our definition of u, and we're going to plug the x values into that to find new bounds. So 1 plus 0 cubed is just 1. That is now our new lower bound. Our new upper bound, we just take x equals 2, plug that in, okay, for x. 1 plus 2 cubed is 9. That's now our upper bound. And then all this stuff at the beginning that we worked on kind of just goes away. We have a new problem to do, and this is all we focus on. So add 1, divide by it for our function. We get 2/3 times u to the 3/2 evaluated on our new bounds, 1 to 9. So f of 9 minus f of 1, and clean it up. 52/3. You're done. Don't ever bring in the x's again. Let's try part B. We'll have u equals 1 plus 5x squared. Du equals 10x dx. We're pretty close. That 10 needs to be divided out though. So our new problem is going to be 1/10 u to the -1 du. Now let's work on our bounds, okay? So we'll take our lower bound of 0 and plug it into this part to find the new u bound. 1 plus 0 is 1. Now we'll take the upper bound of 1, plug it in, and we'll find a new upper bound of 6. And notice I've kind of grayed out the top. We don't go back there again. Just solve the new problem. U to the -1, that's the same as 1 over u. So the antiderivative of that is the natural log of u. F of 6 minus f of 1 times 1/10, and you're done. If you want to clean that up a little bit more, the ln of 1 is 0, so that's a little bit prettier. Or trig functions. What do you think u should be? We've got tangent x and secant squared x. Well, secant squared x is the derivative of tangent x. Aha! U equals tangent x. Du equals secant squared x dx. Change our bounds. So instead of x equals 0, we need the tangent of 0, which is 0, so that one stayed the same. And then instead of pi over 4, we need tangent pi over 4, which is 1. So here's our new problem. 0 to 1, u du. Now, doesn't that look way simpler than our original problem? Add 1, divide by it. So we get 1/2 u squared evaluated from 0 to 1. 1/2 times f of 1 minus f of 0. It's just 1/2. Part D looks horrible and scary, doesn't it? So what are we going to do with that one? What would u be? What's an inside function? Now, 2 theta is an inside function. So if we said u equals 2 theta, du would equal 2 d theta. We haven't gotten very far, so that's, I think, too much of an inside function. Let's try something different. What if it's cosine of 2 theta? Okay, so now du is negative 2 sine 2 theta d theta. So the derivative of cosine is negative sine, keeping the inside the same, and then using chain rule, the derivative of 2 theta is 2. And look at, we've got our sine 2 theta d theta right here, so that's good. We just got to get rid of that negative 2. Pull that negative 1/2 to the front, and then we're going to change our bounds. So if x equals 0, we'll plug that in here. So cosine 2 times 0 is cosine of 0, which is 1. Pi over 6, cosine 2 of those, so cosine pi over 3 gives us 1/2, and now we have our new problem. But I see a problem. Our lower bound is 1, and our upper bound is 1/2. 1 is bigger than 1/2, so we're kind of going backwards here. So I'm going to have to switch those. Okay, when I switch those, I have to pull out a negative, which is going to make that a positive. Now I can solve the problem. Add 1 and divide by it. I've got 1/2. That's the guy on the outside here. And then negative 1/2, u to the negative 2, evaluated from 1/2 to 1. And I ran out of room, so I'm just telling you, it's 3/4. Two more algebraic techniques that can be used in integration are long division and synthetic division, and completing the square. We're going to talk about completing the square next time. But before we leave today, let's do a quick review of long division and synthetic division. Long division or synthetic division are used when the numerator has a degree that is greater than or equal to the denominator. So check this out. So the numerator has a degree of 3, the denominator has a degree of 1, and there's really no way to separate that fraction. So we'll just divide it. Do you remember synthetic division? This guy, okay, we pull the negative of him into this box here, and then we take the coefficients of each of our terms in the top. 1, 3, -1, -3. Then we start by pulling the 1 straight down, multiply it times my box, so -1 times 1 is -1. Now these numbers, add them together and repeat the process. -1 times 2 is -2. Add these guys together. You get -3. -1 times -3 is 3. And we get this lovely remainder of 0. So here's my new polynomial. X squared plus 2x minus 3. That you can take the antiderivative of. 1/3 x cubed plus x squared minus 3x, don't forget your constant of integration, plus c. Okay, let's try long division. Has it been a while since you've done long division of polynomials? So first we get our division sign. Whatever's on the bottom goes on the outside, and whatever's on the top goes on the inside. All right, now how do we do this? We have to figure out, what do I multiply 3x by to get 3x squared? That would be x. Now I take the x and multiply it by each of the terms on the outside. So I get x times 3x is 3x squared. Yay, that's what we wanted. And then x times -7 is -7x. Then you subtract that quantity, and we get 6x, and bring the 21 down. Now we do that process again. What do I need to multiply by 3x to get 6x? 2. And then the 2, I multiply by each of the terms on the outside. So 2 times 3x is 6x. Yay! 2 times -7 is -14. subtract that quantity. Oh dear, I have 35. That's not a zero remainder. I have a new polynomial, x plus 2, plus this remainder is still over 3x minus 7. The one on the left isn't going to be a problem. The antiderivative on the right, we'll have to use U substitution, okay? U equals 3x minus 7. du equals 3x. So this 1/3 will come out with the 35 on top, so 35 over 3. And then we'll integrate this guy. 1 over u becomes ln of the absolute value of u. And we'll just kind of keep plugging this guy along with us. What is u? We'll have to plug that back in. There's no bounds to change, so in this case, we do have to get our x plugged back in. And there's our final answer. 1/2 x squared plus 2x plus 35 over 3, natural log of the absolute value of 3x minus 7 plus c. If you're feeling a little bit overwhelmed by U substitution, that's okay at this point. It does take practice finding those inside functions to make U, but once you can locate U, I think the rest of it becomes smoother and smoother as you practice. Thank you so much for hanging in there with me.